Hey guys, welcome back. Today we're going to talk about another type of energy, and that is kinetic energy. Now, kinetic energy is the energy of motion. That is, any moving object has some energy that might be able to do work, or cause some damage, or make some sound, or release some heat, or so on. Now, the formula for kinetic energy has a couple factors in it. Let's see if we can think about what those might be. I would think that an object that is bigger or more massive probably can do more damage or have more energy stored in it than something else. I would think also maybe the speed would be involved. In fact, that's really it for factors. The formula is, as listed here, half of mass times velocity squared. Notice that's symbolized with the letters KE. And I want you to notice that in this particular formula, velocity ends up being a more important factor than mass because it's squared. Notice also the factor of 1/2. For those of you who aren't really into mathematical equations, you can think of the 1/2 as, say, a fudge factor to make the calculations work out right. But for those of you who are more into math, you might understand that kinetic energy is the integral of momentum, or momentum is the derivative of kinetic energy. Anyway, math dorks unite. Let's go. Alright, let's look at an example. But before I do, I did promise that I would say hi to one of my students. So, hi Jess. Now, how much energy is there in, say, one of those boys that you might be babysitting and he's just running around and bouncing off the walls and everything? I mean, really, seriously, how much energy does he have stored up in him? So to make this calculation, let's use the formula. Kinetic energy is equal to 1/2 times the mass times the velocity squared. So if we start to plug in some numbers, a mass of 30 kilograms, that's the standard unit of mass, and meters per second is the standard unit of velocity. That's squared. So 1/2 times 30 times 4 times 4. I get 240 joules. Now, just for comparison's sake, let's say he runs maybe twice as fast. How much energy does he have now? 480? Well, a half. He's still the same mass. But suppose he's running twice as fast, that would be 8 meters per second. And when we square that, notice we get 960, which is actually not twice as much energy, but 4 times as much energy. In general, when you double the velocity of an object, you quadruple the amount of kinetic energy that object has. That's different than momentum, where there's a one-to-one relationship. Now, how much energy would he have if we just got sick of him, we tied him up, and we threw him on a 3-meter high shelf? Well, the type of energy he would have now is just potential energy. So, potential energy, and the formula for that, if you remember, was mgh. And the amount of mass he has is still the same, 30. The gravitational constant is 9.8 in the metric system, and the height was 3. And these calculations work out to 882. So he'd have a whole lot more energy if we tied him up than if we just let him run around. Now I would like to do an example that kind of begins to show the power of using energy in calculations. What I'd like to know is how fast that boy might be moving if he fell from the 3-meter high shelf. Now, we could calculate this with the old kinematics equations, but it's kind of difficult because we have to figure out how much time it takes for him to hit the ground and then use the so-volt for AT&T formula or something to figure out that distance or that velocity. It's just ugly. When working with energy, it's much simpler. Here's the key idea that might help. First of all, the boy begins with potential energy, which could become kinetic energy as he falls. Once he hits the ground, this transfer is completed. And we usually write this with the symbol PE is converted into KE. This relationship suggests a good equation to use as a starting point, and that is, let's set all of that potential energy equal to kinetic energy. Now, we just calculated the amount of potential energy he would have on the shelf. That was 882. And let's use the kinetic energy formula, 1/2 times m times v squared. And we're trying to figure out the speed. We know the mass, and you can see with this equation, it's actually very quick to calculate. 1/2 of 30 times v squared. Half of 30 is 15. And so let's divide both sides of this equation by 15 and then take the square root. V will be the square root of 882 over 15. So square root 882 over 15, the closing parenthesis, and that's equal to 7.6 meters per second. Now, this relationship and this quick calculation of how fast an object is going after it's fallen a certain distance is so useful that it's worth doing once with no variables at all and coming up with a formula for it. So, calculate the speed that an object is moving after falling a certain distance, assuming that all of the potential energy that it has gets converted into kinetic energy. So, whenever this assumption can be made, that all the potential energy of an object becomes kinetic energy, we would start off with m times g times h, and that's equal to 1/2 of mv squared. Notice here that in general, the mass of the object doesn't matter, and so if it was a 60 kilogram kid instead of a 30 kilogram kid, either way, the mass on either side would cancel out, and we would end up with the same velocity. Now, that's not true if you have to start taking air friction into account, but if you have to start taking air friction into account, then this original equation, that all the potential energy gets converted into kinetic energy, won't be true either. So, if I multiply both sides by if I multiply both sides by 2, that will get rid of the factor of 1/2. So 2 times gh, and 2 times 1/2 cancel it out, so I'm left with just v squared. And if I take the square root of both sides, we get a formula that the velocity of a falling object is equal to the square root of 2 times g times h. Let's see if we can use this formula to calculate the same thing that we got just a second ago. For a boy falling off the shelf, we can put in the square root of 2, and in the metric system, gravity is 9.8, and the height was 3. So square root of 2 times 9.8 times 3, and we get the exact same number. So that's just a preview of some of the many different equations and relationships that we can say about different types of energy. So that's it for kinetic energy. Tune back in soon for another video on another type of energy, which is the potential energy stored in a spring. And we'll also soon be doing a couple videos on the conservation of energy, which is more about the relationships between types of energy and when one gets converted to another, what sort of equations and formulas we can derive. Thanks for watching.